In the realm of self-supervised learning, the concept of quantifying representation reliability in models has emerged as a crucial consideration. This is because many downstream models rely on these representations as input for their tasks, and their accuracy can significantly impact the outcomes. Representation reliability is formally defined as the ability of downstream models to consistently generate accurate predictions for a given test point. However, accessing downstream data to quantify representation reliability is often infeasible due to privacy concerns. To address this, an ensemble-based method for estimating representation reliability without knowing the downstream tasks a priori has been proposed. This method is based on the concept of neighborhood consistency across distinct pre-trained representation spaces. The key insight is to find shared neighboring points as anchors to align these representation spaces before comparing them. Estimating representation reliability is crucial for ensuring the trustworthiness of pre-trained models in various applications. This research proposes an ensemble-based approach to quantify representation uncertainty without prior knowledge of downstream tasks. The method is rooted in the concept that a test point has a reliable representation if it has a reliable neighbor that remains consistently close across multiple representation spaces generated by different embedding functions. To achieve this, the approach computes the number of consistent neighboring points among the reference data. This metric serves as a proxy for representation reliability, enabling the comparison and ranking of pre-trained models based on their reliability scores. The proposed method is extensively validated through numerical experiments, demonstrating its superior performance in capturing representation reliability compared to existing baselines. The significance of this work lies in its potential to facilitate the responsible deployment of pre-trained models. By providing a reliable measure of representation uncertainty, practitioners can make informed decisions when selecting models for specific applications. This, in turn, can lead to more robust and trustworthy AI systems. The proposed approach offers a critical step towards this goal, enabling the development of more reliable and generalizable pre-trained models. The authors of the research paper delve into a comparative analysis of their approach with existing works in out-of-distribution detection and uncertainty quantification in self-supervised learning. They emphasize the novelty of their method, which extends the concept of a probe to multiple downstream tasks without any prior knowledge about the specific tasks. The paper highlights the growing body of research in uncertainty-aware representation learning, aiming to train robust self-supervised models that map input points to a distribution in the representation space. In contrast to existing methods that rely on special neural network architectures or alternative training schemes, the author's approach is distinguished by its theoretical analysis and exploration of the impact of representation reliability on downstream tasks. The authors revisit the Bayesian inference view of epistemic uncertainty in supervised learning, where a prior probability distribution is introduced, and a posterior distribution is learned given a training dataset. They explain how the posterior predictive distribution is obtained by averaging predictive probabilities over models, and how Monte Carlo approaches, such as deep ensembles, can be used to approximate the integral. The authors introduce the concept of uncertainty quantification in supervised learning, where uncertainty can be assessed by the inconsistency of output across sampled functions. They provide equations for quantifying uncertainty, such as variance for regression tasks and entropy for classification tasks. Finally, the authors present their framework for assessing the reliability of representations assigned by pre-trained models, defined as the consistency of neighboring points in the representation space. They emphasize the limitations of existing uncertainty quantification frameworks in supervised learning when applied to representation spaces and present an ensemble-based method that effectively captures representation reliability without prior knowledge of downstream tasks. Evaluating the quality of representations from pre-trained backbone models is crucial, and two key concepts are essential in this assessment: representation reliability and neighborhood consistency. Representation reliability refers to the average performance of downstream models when utilizing these representations. This metric provides a comprehensive understanding of a representation's quality, as it aggregates the performance of multiple models. Neighborhood consistency, on the other hand, measures the number of consistent neighbors among reference points across different representation spaces. This concept is vital, as it helps identify representations that are robust and consistent across various embedding functions. The authors demonstrate that neighborhood consistency can be estimated by analyzing the number of consistent neighbors, which is critical in evaluating representation quality. Notably, the authors also present a negative result, highlighting that different embedding functions can produce inconsistent representations yet yield consistent downstream predictions. This finding underscores the importance of considering both representation reliability and neighborhood consistency when evaluating the quality of representations. This research lays the foundation for estimating representation reliability without prior knowledge of downstream tasks, a crucial step in developing more effective and efficient representation learning methods. By understanding the relationship between representation reliability and neighborhood consistency, researchers can develop more robust and reliable representations, ultimately leading to improved downstream model performance. The authors propose a novel framework to address the issue of non-unique representation spaces in deep learning models. They introduce the concept of an anchor point, which serves as a bridge to align different representation spaces, ensuring that downstream predictions are bounded above by a certain variance. This idea is formalized in Theorem 2, which states that if a test point has a consistent neighboring point across all representation spaces, then the uncertainty of its downstream predictions is bounded above. The theorem is proved in Appendix A.2, and it is extended to the multi-output case. The key takeaway is that finding a reliable reference point consistently close to the test point can serve as an anchor point, aligning representation spaces with distinct semantic meanings. The reliability of the reference point and its relative distance to the test point ensure a lower bound on the representation reliability of the test point. In practice, identifying a single reliable reference point is challenging without prior knowledge of the downstream tasks. Instead, the authors propose drawing a set of reference points, denoted as xref, and computing the number of consistent neighboring points within xref to estimate the representation reliability. The neighborhood consistency, NC, of a test point X is defined as the similarity between the sets of nearest neighbors of high X among high X element of xref across different embedding functions. The parameter k involves a trade-off between choosing a neighborhood closer to the test point and increasing the chance of incorporating a more reliable neighbor. A large k may result in selecting a reliable neighbor, but it could be far from the test point, while a small k may compromise the reliability of the selected neighboring point. The authors of the research paper present a comparative analysis of their proposed neighborhood consistency method, denoted as NC100, with 4 baseline methods: dist, norm, LL, and feature variance, FV. This comparison is based on the correlation of each method with the representation reliability, measured using Kendall's tau coefficient. The results are presented in Table 1, which displays the correlation scores for each method on various downstream tasks, including in-distribution tasks where the model is pre-trained and fine-tuned on the same dataset. The performance on these tasks is evaluated using either negative predictive entropy or negative Breyer score. NC100 consistently achieves a favorable score compared to the baseline methods across different architectures and datasets. Specifically, NC100 outperforms the baseline methods on ResNet 18 and ResNet 50 architectures for CIFAR10 and CIFAR100 datasets. The baseline methods are described as follows. Dist is the average of the k-minimum distances from the test point to the reference data in the representation space. Norm is the L2 norm of the representation. LL is the log likelihood of the Gaussian or von Mises-Fisher mixture models on the test point when fitted on the reference data. And FV is the representation consistency measured by the variance of neural networks' predicted scores. To ensure a fair comparison, the authors employ an ensemble average of each score over different embedding functions for dist, norm, and LL. They also randomly select 5,000 pre-training data as the reference dataset and repeat the experiments 5 times with distinct random seeds to report the average evaluation scores. The hyperparameters used in the experiments include k equals 100 for NCK and k equals 1 for dist k, with both cosine distance and Euclidean distance as options for the distance metric. The authors also evaluate LL and FV using both unnormalized and normalized representations. The implications of these selections are discussed in section 4.5 of the paper. The correlation between representation reliability and downstream classification tasks is a critical area of study, particularly in in-distribution and transfer learning scenarios. Our analysis reveals that NC100 consistently demonstrates a higher correlation with representation reliability compared to baseline models, as shown in tables 1 and 2. This suggests the superior performance of NCK over baselines in identifying unreliable representations. The use case section exemplifies how NC can be utilized to rank pre-trained models based on their reliability scores, providing a valuable tool for selecting the most suitable model for specific downstream tasks. This approach highlights the effectiveness of NC in quantifying the reliability of individual embedding functions, which is essential for optimizing model performance and ensuring accurate predictions. In conclusion, the importance of NC in enhancing our understanding of representation reliability cannot be overstated. By leveraging this metric, researchers and practitioners can develop more robust and efficient machine learning models, ultimately leading to improved outcomes in various applications. The authors present a comparison of their neighborhood consistency, North Carolina 100, method with baseline methods in terms of their correlation with representation reliability. The experiment involves pre-training embedding functions on tiny ImageNet and fine-tuning on CIFAR10, CIFAR100, and STL10 datasets. The results in Table 2 show the correlation coefficients between the NC100 method and the baseline methods, including entropy, Brier, norm, LL, and FV, using ResNet 18 and ResNet 50 architectures. The NC100 method demonstrates a strong correlation with representation reliability, outperforming most baseline methods. Specifically, the NC100 method achieves correlation coefficients ranging from 0.1224 to 0.2557, indicating a positive relationship between the NC100 scores and the representation reliability. Table 3 presents a comparison of the NC100 method with baselines in selecting reliable backbones among those pre-trained by three algorithms, SimCLR, BIAL, and MoCo, on the tiny ImageNet dataset. The results show that the NC100 method achieves high Kendall's tau coefficients, indicating a strong correlation between the rankings given by the NC100 method and the actual downstream performance. The authors also discuss an approach to augment the embedding function space by applying the same learning algorithm with varying random seeds and data used to train the original embedding function. This approach is validated in tables 10 and 11 in Appendix C, demonstrating that the NC100 method can effectively predict the reliability of individual embedding functions. Additionally, the authors conduct ablation studies to investigate the robustness of their method to the choice of distance metric and ensemble size. The results show that the NC100 method consistently demonstrates a positive correlation with representation reliability, regardless of the distance metric chosen, and that increasing the ensemble size improves the correlation scores. Evaluating the quality of representations in self-supervised learning is crucial for ensuring the trustworthiness and responsibility of pre-trained models. This study introduces a mathematical definition for representation reliability, a key concept in this context. Existing uncertainty quantification frameworks are inadequate for estimating uncertainty in representation spaces, prompting the derivation of a novel estimate for representation reliability. The proposed method, Neighborhood Consistency, NCK, effectively captures representation reliability and exhibits a positive correlation with it across different settings. NCK outperforms baseline methods in terms of correlation with representation reliability and downstream performance. A key finding is that a small ensemble size of M equals 2 can achieve competitive performance with larger ensembles, highlighting a trade-off between the number of neighbors, K, and ensemble size, M. This study underscores the importance of considering representation reliability when evaluating self-supervised learning models. Future research should prioritize ensuring the responsibility and trustworthiness of pre-trained models, including making representations interpretable, robust against adversarial attacks, and incorporating a notion of uncertainty. Potential future directions include expanding the approach to avoid the need for training multiple embedding functions and extending the definition of representation reliability to cover a broader range of downstream tasks. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. In the realm of machine learning, several research papers and techniques have garnered significant attention. This summary focuses on contrastive self-supervised learning, Bayesian representation learning, and uncertainty estimation. A seminal work in this field is a survey by Ashish Jaiswal et al., which provides a comprehensive overview of contrastive self-supervised learning. This technique has shown promising results in various applications, leveraging the idea that models can learn from contrasting positive and negative samples. The survey delves into different architectures, loss functions, and evaluation metrics used in this approach. Another key area of research is Bayesian representation learning, which aims to model uncertainty in the learned representations. This approach integrates principles from Bayesian inference to quantify the uncertainty associated with the model's predictions. By accounting for this uncertainty, models can become more robust and adaptable to unseen data. Uncertainty estimation is another crucial aspect of machine learning research. It involves quantifying the model's confidence in its predictions, allowing for better decision-making and risk assessment. Techniques such as deep ensembles and Monte Carlo dropout are commonly used to estimate uncertainty in neural networks. These techniques are not mutually exclusive. They often complement each other in real-world applications. For instance, contrastive learning can be used to pre-train models that are then fine-tuned using Bayesian representation learning techniques. Similarly, uncertainty estimation can provide insights into the reliability of the model's predictions, enhancing overall performance. The interplay between these research areas is multifaceted and complex. Each technique contributes to a deeper understanding of how machines learn and represent data, ultimately leading to more accurate and reliable models. As research continues to evolve, integrating these techniques will likely play a pivotal role in advancing the field of machine learning. In their 2020 paper, Yeming Wen, Dustin Tran, and Jimmy Ba proposed the batch ensemble method as an alternative approach to efficient ensemble and lifelong learning. This method addresses the challenges of traditional ensemble methods, which often require significant computational resources and memory. The batch ensemble approach utilizes a shared base network across all ensemble members, reducing the memory footprint while maintaining the performance of traditional ensembles. This innovative technique has implications for various applications in machine learning and deep learning, particularly in scenarios where computational efficiency is paramount. Theorem 3 presents a theoretical result that builds upon Theorem 1, considering downstream tasks as prediction tasks. It states that for any test point x** operator and a given downstream task t, there exist embedding functions h1, h2m such that the variance of the representation of x** operator under each embedding function is at least a, but the variance of the downstream prediction under each embedding function is 0. The proof of Theorem 3 begins by assuming only two embedding functions, h1 and h2, without loss of generality. 2 points z1 and z2 are selected in the representation space Z, with the Euclidean distance between them being at least diam, z, delta, where delta is a small constant. The embedding functions h1 and h2 are then defined to satisfy the condition that high x** operator equals z and h1 equals a hollow bullet h2, where A is an invertible matrix. This construction ensures that the variance of the representation of x** operator under each embedding function is at least diam z delta 2 halves. The proof also demonstrates that G1 T hollow bullet A is an optimal downstream head for H2 under task T, where G1 T is an optimal downstream head for H1 under task T. This is achieved through contradiction, assuming that there exists another downstream head G2 T that achieves higher performance than G1 T hollow bullet A when combined with H2. The contradiction arises from the fact that G2 T hollow bullet A*1 can achieve higher performance than G1 T when combined with H1, which contradicts the optimality of G1 T. Finally, the proof extends to the case of 2M embedding functions by setting H2 I1 x** operator equals Z1 and H2I, X asterisk operator, equals Z2. The graphical visualization of the sketch for the proof of Theorem 2 is provided in Figure 3, illustrating the idea of using a reliable neighboring point XR as an anchor for comparing different representations of the test point X asterisk operator. This section of the research paper presents a proof for Theorem 2, which is a pivotal component in the overall argument. The theorem statement and proof are not provided here, but it is clear that the authors are working with neural networks and their properties. The proof begins by introducing a new notation, phi equals gi, t hollow bullet high, to simplify the expression. It then proceeds to establish an upper bound for the output difference between two functions phi, x asterisk operator, and fj, x asterisk operator, using the triangle inequality. This bound involves the Lipschitz constant Lt, the error term enb, and the average pairwise L2 squared difference across the ensemble of functions, denoted as sigma r, t. The authors also provide a visualization of this proof sketch in Figure 3, which helps illustrate the relationships between these different components. In addition to the proof, the authors present a lemma that demonstrates the Lipschitz continuity of neural networks. Specifically, they show that for a fully connected layer GL, Z equals a WTLZ plus BL of a downstream predictor, the similarity of outputs is bounded above by the Lipschitz continuity. This result is crucial for understanding how neural networks behave and how their outputs can be controlled and predicted. The proof of the lemma involves applying the triangle inequality and the fact that the activation function A is one Lipschitz continuous. The final result, parallel GL, Z, GL, Z asterisk operator, parallel 2 is less than or equal to parallel WL parallel 2 parallel ZZ asterisk operator parallel 2, demonstrates the Lipschitz continuity of the neural network layer. Overall, this section of the paper provides a detailed proof of Theorem 2 and a lemma on the Lipschitz continuity of neural networks. These results contribute to the paper's main argument and are essential for understanding the properties and behaviors of the neural networks under consideration. In this section, the authors investigate the relationship between the absence of consistent neighbors and the reliability of a test point in a neural network. They present two cases. One where the test point has no neighboring points, and another where it has neighboring points but they are not consistent. The first case is based on the assumption that out-of-distribution points are more likely to be unreliable, implying that if a test point does not have any neighboring points, it is likely out of distribution from the reference points and thus unreliable. The second case involves using the bi-Lipschitz continuity of the downstream predictors and the embedding functions to show that if a test point has inconsistent neighboring points, it is also unreliable. This is achieved by bounding the differences in representations and predictions across different embedding functions, ultimately leading to a contradiction when assuming the test point is reliable. The authors conclude that when a test point lacks consistent neighboring points, it is likely to be unreliable. This insight contributes to understanding the importance of neighborhood consistency in evaluating the reliability of predictions in neural networks. The representation reliability, ReLI, X asterisk operator, H, T, is defined as the average performance of a set of downstream tasks, T, with respect to a given input X asterisk operator and a collection of embedding functions, H. This section explores methods for computing representation reliability using standard uncertainty or accuracy measures. In regression tasks, the negative variance of the predictive distribution can be utilized as a performance metric, perf T, GH, T hollow bullet H, X asterisk operator, equals minus var, GH, T hollow bullet H, X asterisk operator. This metric can be approximated using an ensemble of embedding functions, H1, HM, and the corresponding downstream predictors, G1, T, GM, T. The approximation is given by equation 27, which computes the average squared difference between the predictions of each embedding function. In multi-output tasks, the trace of the covariance matrix can be used as a performance metric, which aggregates the individual uncertainties of each output dimension. For classification tasks, metrics like the Breyer score or entropy are more natural choices. The negative Breyer score and negative entropy are calculated using equations 28 and 30, respectively, which utilize the softmax output of the predictive function and the ground truth label. Empirical studies have demonstrated a strong correlation between uncertainty and predictive accuracy. Theorem 2 establishes a lower bound of the representation reliability measured by perf t equals minus var, which is assured by the sum of the reference point's reliability along with its relative distance to the test point. This explains how the NC score could effectively capture representation reliability, irrespective of the specific performance metrics employed. Additional experimental results. Multiclass downstream classification tasks. The evaluation protocol employs 1 vs 1 OVO binary classification tasks for downstream evaluation. The average performance across OVO tasks is expected to correlate well with that of the multiclass classification task. In the context of multiclass classification tasks, empirical studies are conducted on the original multiclass setups to validate the assumption that the proposed method is effective. The key distinction from the original protocol is that the number of tasks is set to 1, and the output size for the linear heads corresponds to the number of classes C, which is 10 for CIFAR10 and STL10 datasets, and 20 for CIFAR100 using coarse labels. The results, presented in Table 5, exhibit a consistent trend with previous observations. Furthermore, the efficacy of the proposed method is explored with unnormalized representation, such as Euclidean distance instead of cosine distance. The results, presented in Tables 6 and 9, demonstrate consistent and strong performance even when utilizing unnormalized representation, whereas baseline methods suffer from a significant performance reduction. This is attributed to the fact that points with a larger L2 norm tend to exhibit higher reliability, and reliable points are often located in the outer regions of the representation space, resulting in larger distances between points in those regions compared to points near the origin. Ablation studies are also conducted to explore various combinations of pre-training algorithms, model architectures, and datasets, with the Breyer score used as the downstream performance metric. The results are presented in Figures 4 and 5. Additionally, the paper investigates whether the NC score can be applied to gauge the reliability of individual embedding functions H element of H. The correlation between the measures and the representation reliability estimated with Breyer score is measured for each member of the ensemble. The results, presented in Tables 10 and 11, include the average correlation and its standard deviation across the individuals. Non-ensemble scores are also reported for metrics such as dist1, norm, and LL, which are inherently applicable to individual embedding functions without using the ensemble. A comparative analysis of pre-training algorithms, including SIM-CLR, BIAL, and MoCo, is presented across different architectures, ResNet18 and ResNet50, and datasets, CIFAR10 and CIFAR100. The neighborhood consistency metric NC100 is used to evaluate the quality of learned features for downstream tasks. A correlation analysis between neighborhood consistency and in-distribution task performance reveals that MoCo exhibits the highest correlation on ResNet18, with SIM-CLR and BIAL following closely. MoCo's features are most predictive of success in downstream tasks, as measured by entropy and Breyer score. When using ResNet50, MoCo again leads, although SIM-CLR and BIAL are not far behind. Notably, MoCo's correlation decreases slightly when moving from ResNet18 to ResNet50, while SIM-CLR and BIAL experience an increase. Feature normalization, represented by the norm column, generally improves the correlation, especially for MoCo, suggesting that normalizing features can enhance the predictive power of neighborhood consistency. The LL and FV columns compare the correlation when using linear logistic regression and fine-tuning, respectively. Fine-tuning generally results in higher correlations, indicating that adapting the model to the specific task can improve its performance. However, the difference is less pronounced for MoCo, which already performs well without fine-tuning. This analysis demonstrates the importance of neighborhood consistency as a metric for evaluating feature quality during pre-training and highlights MoCo's ability to learn highly predictive features, especially when combined with feature normalization and fine-tuning. The table presents a comprehensive comparison of the correlation between the neighborhood consistency metric, North Carolina 100, and performance on in-distribution downstream tasks for multi-class classification tasks. It showcases results for 3 pre-training algorithms, SIM-CLR, BIAL, and MoCo, divided into 2 sections for ResNet 18 and ResNet 50 architectures. For each architecture, the correlation coefficients are reported for 5 methods: NC100, DIST1, Norm, LL, and FV, evaluated on 2 datasets, CIFAR10 and CIFAR100. The results demonstrate that NC100 consistently outperforms baseline methods in terms of correlation with downstream task performance. Specifically, NC100 achieves the highest correlation coefficients for both ResNet 18 and ResNet 50 architectures, across both datasets. For ResNet 18, NC100 achieves a correlation coefficient of 0.3848 for CIFAR10 and 0.2998 for CIFAR100, significantly outperforming baseline methods. Similarly, for ResNet 50, NC100 achieves a correlation coefficient of 0.3756 for CIFAR10 and 0.2969 for CIFAR100, outperforming baseline methods. These results suggest that the proposed NC100 metric is a reliable indicator of downstream task performance and can be effectively utilized for pre-training algorithm selection. The consistent outperformance of NC100 across different architectures and datasets underscores its robustness and generalizability. In the context of pre-training and its impact on in-distribution downstream tasks, this study conducts a comparative analysis of the neighborhood consistency, North Carolina 100, method against baseline algorithms. The analysis employs 2 distinct architectures, ResNet 18 and ResNet 50, to evaluate the performance of SIM-CLR, BIAL, and MoCo algorithms across various metrics, including entropy, Brier score, and their normalized counterparts. The results, presented in Table 6, highlight the correlation between NC100 and baseline methods for both architectures. Notably, for ResNet 18, SIM-CLR and MoCo consistently outperform baseline methods in terms of NC100, demonstrating a stronger correlation with in-distribution task performance. BIAL also exhibits robust performance, albeit with a weaker correlation. In contrast, for ResNet 50, all algorithms exhibit weaker correlations compared to their ResNet 18 counterparts, although MoCo continues to lead in terms of North Carolina 100. The table also provides insights into the algorithm's capabilities and limitations through additional metrics, including distance, DIST1, normalized, norm, linear layer, LL, and feature vector, FV, methods. These metrics are particularly informative when considering the unnormalized representation used in this analysis. The findings suggest that the choice of architecture significantly influences the effectiveness of pre-training algorithms, with ResNet 18 generally yielding better results. Moreover, the study emphasizes the importance of considering multiple evaluation metrics to gain a comprehensive understanding of an algorithm's performance and potential for real-world applications. This analysis contributes to the development of robust pre-training algorithms by providing detailed comparative insights into the strengths and weaknesses of various methods. Table 7 presents a comprehensive comparison of the correlation between the proposed neighborhood consistency metric, NC100, and various baseline methods across 3 transfer learning tasks: Tiny ImageNet to CIFAR10, CIFAR100, and STL10. The results are reported for both ResNet 18 and ResNet 50 architectures. The correlation coefficients between NC100 and baseline methods, including entropy, Brier, norm, LL, and FV, are calculated for each transfer learning task and reported with their corresponding standard deviations. Notably, SIM-CLR with NC100 achieves the highest correlation coefficients with entropy and Brier scores across all 3 transfer learning tasks for ResNet 18. BIAL with NC100 also exhibits strong correlations, particularly with entropy scores. For ResNet 50, SIM-CLR with NC100 maintains high correlation coefficients with entropy and Brier scores, while BIAL with NC100 exhibits strong correlations with entropy scores. MoCo with NC100 demonstrates moderate correlations across all tasks for both architectures. In contrast, DIST-1 and norm baselines exhibit weaker correlations with NC100 across all tasks and architectures. The LL and FV baselines generally exhibit negative correlations with NC100, indicating their limited effectiveness in capturing neighborhood consistency. These results suggest that the proposed NC100 metric is effective in capturing the neighborhood consistency of self-supervised learning methods and can be used as a reliable indicator of their performance on transfer learning tasks. The comparative analysis presented in the table shows a positive correlation between neighborhood consistency, North Carolina 100, and the SIM-CLR algorithm across CIFAR10, CIFAR100, and STL10 datasets using ResNet 18 and ResNet 50 architectures. This suggests that SIM-CLR effectively enhances the neighborhood consistency of pre-trained models, potentially improving their performance on downstream classification tasks. In contrast, other baseline methods exhibit varying levels of correlation, often showing negative values or lower positive correlations. The choice of architecture influences the effectiveness of these algorithms, with ResNet 50 showing higher values for SIM-CLR. This study highlights the potential benefits of utilizing algorithms like SIM-CLR that prioritize neighborhood consistency, offering insights into the role of neighborhood consistency in transfer learning tasks. This table presents a comparative analysis of the neighborhood consistency, North Carolina 100, between our proposed method and baseline algorithms, including SIM-CLR, BIAL, and MoCo, on transfer learning tasks from TinyImageNet to CIFAR10, CIFAR100, and STL10. The comparison is conducted using two different architectures, ResNet 18 and ResNet 50. For ResNet 18, the results indicate that our method outperforms the baseline algorithms in terms of neighborhood consistency across all three target datasets. Specifically, our method achieves a higher correlation with the performance on transfer learning tasks compared to SIM-CLR, BIAL, and MoCo. This suggests that our approach better captures the relationship between neighborhood consistency and performance in transfer learning. In the case of ResNet 50, the trends observed are similar, with our method showing superior neighborhood consistency and a stronger correlation with transfer learning performance. However, the differences in performance are less pronounced compared to ResNet 18, indicating potential limitations of our approach when applied to deeper architectures. The table also provides insights into the performance of each algorithm on different target datasets. For instance, our method exhibits higher neighborhood consistency and stronger correlations with transfer learning performance on CIFAR10 and STL10 compared to CIFAR100. This could be attributed to differences in dataset complexity and the nature of the tasks involved. Furthermore, the table highlights the importance of normalizing the representation in enhancing neighborhood consistency and transfer learning performance. Normalization significantly improves the correlation between neighborhood consistency and transfer learning performance for all algorithms, suggesting that it plays a crucial role in maintaining consistent representations across different domains. Overall, this table demonstrates the effectiveness of our proposed method in capturing neighborhood consistency and its relationship with transfer learning performance. It emphasizes the need for further exploration into the role of normalization and its implications for improving the generalizability of self-supervised learning algorithms. An ablation study is conducted to evaluate the impact of ensemble size on downstream performance in the proposed NCK model and baseline methods. The Breyer score is employed as the downstream performance metric. Results are presented in Figure 4, which displays the performance of the NCK model and baseline methods, including deep ensemble, snapshot ensemble, and stochastic weight averaging, under varying ensemble sizes, m equals 1, 5, 10, 20, 50, on the CIFAR10 dataset. The study reveals that increasing the ensemble size leads to improved performance in the NCK model, with the largest gain observed when moving from m equals 1 to m equals 5. Notably, the NCK model consistently outperforms the baseline methods across all ensemble sizes, although the performance gap narrows as the ensemble size increases. This suggests that the benefits of the NCK model are more pronounced when using smaller ensembles. The ablation study highlights the importance of ensemble size in achieving robust performance. The results imply that the NCK model's ability to effectively aggregate information from diverse models is key to its superior performance, particularly when using smaller ensembles. This reinforces the idea that the NCK model's strength lies in its capacity to adapt to diverse models and ensemble sizes, making it a robust and reliable choice for downstream tasks. Furthermore, the study underscores the importance of carefully selecting the ensemble size based on the specific problem domain and available computational resources. The analysis on the performance of the proposed NCK model involves ablating over the number of neighbors, k. Figure 5 compares the NCK model with baseline methods using the Breyer score as the performance metric. The graph demonstrates the NCK model's varying performance with different k values, showcasing its effectiveness across different neighborhood sizes. This evaluation is crucial for understanding the model's adaptability and robustness in various scenarios. A comparative analysis of neighborhood consistency, North Carolina 100, and baseline methods reveals their performance on in-distribution downstream tasks for a single embedding function. The correlation between NC100 and baseline algorithms, including SIM-CLR, BIAL, and MoCo, is presented across different pre-training models, such as ResNet 18 and ResNet 50. MoCo exhibits the highest correlation with NC100 across both ResNet 18 and ResNet 50 models, indicating strong neighborhood consistency in its pre-training process. SIM-CLR and BIAL demonstrate moderate correlations, suggesting they exhibit some level of neighborhood consistency, although not as strong as MoCo. In contrast, the norm and norm variants of the baseline methods generally show lower correlations, indicating weaker neighborhood consistency. The LL and LL variants exhibit negative correlations, suggesting a lack of neighborhood consistency in these algorithms. FV variants of the baseline methods also show negative correlations, although they are less pronounced than those observed in the LL and LL variants. This analysis provides insights into the effectiveness of different pre-training algorithms in maintaining neighborhood consistency, which is crucial for understanding their performance on in-distribution downstream tasks. The findings highlight MoCo as the most effective algorithm in terms of neighborhood consistency, followed by SIM-CLR and BIAL. The norm, LL, LL, and FV variants demonstrate weaker or negative correlations, indicating potential limitations in their pre-training processes. This comparative analysis explores the correlation between neighborhood consistency, North Carolina 100, and baseline methods in relation to transfer learning performance from Tiny ImageNet to CIFAR10, CIFAR100, and STL10 for a single embedding function. The results are presented for algorithms such as SIM-CLR, BIAL, and MoCo, each with their respective baseline methods dist, norm, LL, and FV. The table illustrates that neighborhood consistency, North Carolina 100, is positively correlated with transfer learning performance across various algorithms and baseline methods. For instance, in the case of SIM-CLR, NC100 shows a positive correlation with all three transfer learning tasks, ranging from 0.1256 plus or minus 0.0031 for CIFAR10 to 0.1485 plus or minus 0.0016 for STL10. Similarly, BIAL and MoCo also exhibit positive correlations, albeit with varying degrees of significance. In contrast, baseline methods like dist, norm, LL, and FV display mixed correlations, some positive, others negative or close to zero. This suggests that these methods may not consistently predict the transfer learning performance as effectively as NC100 does. These findings underscore the importance of neighborhood consistency in enhancing the generalizability of self-supervised learning models. The study's results contribute to understanding the role of neighborhood consistency in improving the performance of these models on unseen data. The authors present an alternative viewpoint on neighborhood consistency, addressing the limitations of existing supervised learning frameworks. They emphasize the importance of comparing abstract representations constructed by different embedding functions in unsupervised learning. To achieve this, a transformation function phi is introduced, mapping different representations into a comparable form. This allows for assessing consistency across a set of representations H using equation 31. The authors discuss the characteristics of an appropriate phi, requiring an anchor to connect different representation spaces. They propose using reliable pre-training data as anchors and introduce a surrogate vector representation, phi rel c, capturing relational information to reference data points rather than absolute location. This surrogate representation can be sparsified using phi relsparse to address information overload. The authors then define the neighborhood consistency measure, NCE, relying on the ENN set notation. However, selecting an appropriate value for E can be challenging, and therefore, a scale-free version of neighborhood consistency, NCK, is introduced, relying on the local nearest neighborhood. The authors propose using either Jacquard similarity or overlap coefficient as set similarity metrics, solely depending on the intersection of the sets when using the KNN approach. In the realm of computer vision, self-supervised representation learning has emerged as a standard practice, involving the training of neural networks to map inputs into latent vectors in the representation space. However, estimating the uncertainty of these learned representations is crucial for creating a reliable machine learning framework. Uncertainty estimation in deep representation learning remains an underexplored area of research. Recently, studies have extended prior deterministic frameworks to stochastic ones, enabling the construction of uncertainty-aware self-supervised representation learning frameworks. For instance, O et al. 2018 introduced the hedged instance embedding, HIB, which optimizes a representation network approximating the distribution over the representation vector p theta z x under the soft contrastive loss and variational information bottleneck principle. HIB's encoder parameterizes the distribution as a mixture of C Gaussians, and the paper proposed an uncertainty metric called self-mismatch probability, interpretable as the expectation of the distance between 2 points randomly sampled from the output distribution. Wu and Goodman, 2020, proposed a similar extension by introducing a distribution encoder that outputs the representation of a Gaussian distribution with a diagonal covariance matrix Saint, X. They extended the normalized temperature-scaled cross-entropy loss, NT-Zent, to a distribution-level contrastive objective, where the norm of the covariance matrix determined by the distribution encoder assesses the reliability of a given input. Despite the benefits of stochastic representation, limitations exist. One major limitation is the requirement for retraining, which can be impractical or infeasible for large models that have been trained on extensive data and require significant computational resources. Additionally, new training schemes can introduce unexpected inductive bias to algorithms already performing well. Furthermore, most probability-based methods rely on standard distributions like the Gaussian or a mixture of them, which may reduce the effectiveness of the model or slow down the training procedure. Another area of research focuses on novelty detection in representation space, where methods detect out-of-distribution (OOD) samples by determining the novelty of the data representation from a deterministic model. These methods commonly use the relative distance information of the query data point's representation vector to other reference points. The dist function computes the average of the k's smallest relative distances in the representation space between the query x** operator and reference points xref, measured by the distance metric dist. This process differs from supervised learning schemes that require instance-specific training labels. For instance, Li et al. 2018 defines an uncertainty score as a minimum Mahalanobis distance to each of the centroids using a tied empirical covariance matrix, whereas Van Amersfoort et al. 2020 calculates a distance using a radial basis function, RBF, kernel. These methods necessitate training labels, which may not always be feasible. Tak et al. 2020 measures the minimum distance between the query instance and all training instances in the representation space to estimate uncertainty in the absence of class label information. Mirzai et al. 2022 averages the distance to nearest instances rather than taking the closest one to improve effectiveness. However, the main limitation of these approaches is the lack of theoretical justification for the proposed metric, as it is founded upon heuristic rules.